Thank you, Bruce. Hello, everyone. My name is Chang Long. My research is focused on scaling those nucleation rates from paradises. So today's talk will be more talk about scaling Benchtop nucleation as well as the prediction for in time. So previously, in the last version, I've demonstrated the next generation of UWA nucleation apparatus, and then demonstrate how we experimentally investigate the system size scaling and confirm that gas-water interface area is appropriate size, appropriate system size for nucleation scaling in KHR-based system. And today's talk will be more talk about introducing the new scaling framework for KHR system, as well as show how we use that framework to predict the induction time, as well as that KHR scaling is not only depends on the system size in terms of gas-water interface area, it also depends on the KHR density, also known as scaling factors. So UWA have produced a lot of meaningful data from the HPS alpha, which is in centimeter scale, as well as the LIB data, which is in millimeter scale. So, but to be more accurately use that industrial relevant data to full line, which will be in kilometer scale. So we're trying to use system size based scaling technique, scale those meaningful data from benchtop scale to field scale. So here is where our pipe alpha system comes in. Hopefully that this apparatus can serve as a bridge to connect the benchtop scaling to full scale. So now I'll briefly introduce our pipe alpha system. So as you see in the left, right-hand side picture, that is how the pipe alpha looks in real life. And those apparatuses are placed in the thermal enclosure so that environmental temperature can be controlled. And left-hand side, the video is showing the structure of this pipe alpha. So here in the middle is the pipe itself. And then we have two pieces of cladding here and there that provide flat surface, so we can attach that temperature control unit on top of that, so we can control the system of temperatures. And here we have stir seat, which hold the magnetic stirring fleece, so then you can provide the mixing ability to the fluid inside the pipe. And we also have two pipe support that holding the whole pipe system on top of the magnetic stir driver. Right, so in this pipe alpha, we're using fast thermoelectric temperature control strategy, which has same principle as what we see in the HPS alpha system. And we also divide that system to three sections, left, middle, and right, to provide a more uniform temperature control. We also have that 4 thermometers directly inserted into the fluid, so we can monitor the fluid temperature more directly. And because of that feature, we have the ability to detect the hydrate formation locally via the temperature signal. And those three stir fleece gives us the ability to vary the mixing speed and location in the system. That will be a really helpful feature when we are investigating the turbulence effect to the hydrate formation. So now I will talk about how we do the experiment here. So in one hydrate formation cycle, we have the system in high temperature. So this plot is showing the temperature change against the time. So when you cool the system temperature to the target temperature, in this case, it will be around 12 degrees C. As you can see, that fluid temperature between 4 thermometers are very close. It's within the 0.2 Kelvin over that half-meter long pipe cell. And the corresponding pressure change is showing here. So within that one cycle of pipe formation, the system will go through the 3 phases. So first cooling, second induction period, and then finally the growth phase. So the hydrate formation we detect based on the sudden pressure jump during the induction time period. So that sudden pressure jump is indicating we have formation in the system. And we also can see that hydrate formation onset from the temperature signal as is in the inset of that temperature change. So that's one cycle of hydrate formation. And then we repeat that procedures over and over again. Then we have a lot of induction time data, given the same subcooling. So we use that induction time data to into a histogram, and then we numerically integrate to yield a cumulative hydrate formation probability, or CDF. So this CDF is what we actually care, and then that's what we're trying to scale from one to the other, because this CDF gives us really useful information. For example, you have certain residence time, and you can find the corresponding hydrate formation probability here. So now we'll focus on how we experimentally investigate that size scaling. So in HPS delta, which is a much smaller system, we observe that the CDF is following exponential distribution. And then even in the much larger pipe alta system, we still see that induction time remains exponentially distributed. And then the next step, when we get these CDFs for different subcoolings, the next step will be extracting that nucleation rate, which Mark explained earlier. How we extract those is based on this equation, which is from classic nucleation theory, which is a very simple equation here. The P represents the formation probability, and J here represents the nucleation rate, and T, which is induction time. So we know from the CDF, we know the probability and we know the induction time. So here, we're just using the nucleation rate as the only adjustable parameters to fit the CDF I showed previously. Then we can extract the nucleation rate for certain or given subcooling or given condition. So if we do that, as you can see in the right-hand side plot there, so those blue triangles are nucleation rate extract from HPS alta systems, and the diamonds from much larger pipe alta system. So as you can see that in larger pipe alta, the nucleation rate is much higher than those in HPS alta, especially at 5K subcooling here. The nucleation rate are 1 order of magnitude higher than we see in HPS alta. So again, so nucleation rate, that is also the one we're trying to scale, because the CDF and the nucleation rate is kind of interchangeable, and we're trying to scale those nucleation rate, because that's also saying, as you can see in the units, that's generally speaking, that's telling you how fast is the hydrate formation happening in the system. So how can we test that size scale? So this cartoon is showing how the pipe cell or pipe alta system looks like when we have 100 ml liquid loading. So the shaded area with the red, that's highlighting the gas-water interface area. And the blue lines over there, the total length of blue lines will be, it's our street-phase contact line where the water, steel wall, and the gas meet each other. So if we change that liquid loading to 300 ml, and that is what happened. So very obviously that the gas-water interface area is getting smaller, much more than the 100 ml liquid loading. But three-phase contact line remains almost the same. So together with the HPS alta system, with these two liquid loading, we have this plot. So we have 3 cases with different system sizes. So from the HPS alta, which have very small gas-water interface area, as well as the three-phase contact line. And then from 2 liquid loading in pipe alta, we changed the gas-water interface area, but three-phase contact line almost remain the same. So now the question is, which one is the better system size for scaling? So you know that nucleation rate is function of subcooling and the temperature. So the idea is very simple. We just divide both sides of the equation by the system size. If that system size is proper one, then your nucleation rate data will be reconstructed altogether. So keep that equation in mind. So the first case I'm showing here is comparison between HPS alta and 100 ml liquid loading. So in this case, both sides, gas-water interface area and the three-phase line increased by a factor of 16. And then we're going to use these two system sizes to scale those nucleation rate we obtained previously. So here, if we scale the nucleation rate with the gas-water interface area, as you can see, all of data align very well with the reconcile. have a very good fit with the classic nucleation theory. And then if we scale with the three-phase contact line, they also seems scale very well, but at the bottom here, the data points are still apart. So in this case, nucleation rate can be very broadly, be scaled by gas-water interface area or three-phase contact line when you're scaling from the HPS alpha to pipe alpha. And then next case will be comparing to different liquid loading in pipe cell, 100 mil and 300 mil. So in this case, the gas-water interface area is only doubled, but the three-phase contact line is really the same. So same strategy, we scale with the gas-water interface area first, and we see they are the nucleation rate points from different loading overlapping very well. But if we scale with the three-phase contact line, they are not as good as the gas-water interface area. So here, that gas-water interface area will be more appropriate system size for scaling between pipelines or when you have very similar geometries. Right. Now I'll be focused on how we unpacking the size scaling of framework for KHI system. So this nucleation report is showing that nucleation rate we obtained from no KHI and a with KHI system. So the left-hand side of your green vertical line, that's the no KHI, right-hand side with KHI. But with KHI, we still observe that half the alpha has much higher nucleation rate than HPS alpha because it's larger. And then, so does that previous scaling technique still work with the KHI? The answer is no. That simple gas-water interface area scaling is no longer working with the KHI system. As you can see in the red line, the nucleation rate data is not reconciled. So that's saying we're missing some scaling factors or missing some information that when we're using that simple scaling technique. So if we plot the induction time we obtain from KHI system against the moles of KHI per surface area, then we will see very interesting situation. So the first here, if you focus on this point, we have 0.58% of KHI in 300 mil liquid loading. That gives you mean induction time more than 10,000 seconds. And if we focus on this point, which has the same KHI concentration but in 100 mil liquid loading, they gives you very small number of moles of KHI per surface area, as well as small numbers of mean induction time, which just above 1,000 seconds. And more interestingly, then you have 0.18% of KHI in 300 mil that have share very similar moles of KHI per surface area, but the mean induction time is just double than the previous points. This factor of 2 is also coincident with the ratio of the gas-water interface area for these two liquid loading. So potentially that may be one of the scaling factors or one of the information that we're missing for scaling KHI system. So the amount of KHI maybe is that one. So now I'd like to introduce my new framework for KHI scaling. So this cartoon is showing KHI solution in our alpha cells. So as you can see that there are free KHI on the back face and on the surface as well. So there will be an equilibrium of that free KHI molecules between back face and the surface. Of course, in a very mixed system. So that free KHI molecules can float between two back face and surface freely. So there will be one equilibrium. So which is all saying the amount of KHI you put in the system is also proportional to the amount of free KHI molecules still in the back face at equilibrium. Right, and interesting here is we have available nucleation size on the surface. And then when you have free KHI molecules floating on the surface, we have a chance that make that free KHI molecules attach on that available nucleation site and block them. So here is the second equilibrium comes here. So free KHI with the nucleation side and plot the available nucleation side. So that the equation showing here, that will be kind of like the first order chemical precipitation reaction in chemistry. So which is saying when those available nucleation sites consume one of the KHI molecules, then you need get more free KHI molecules onto the surface to get those equilibrium happen. So those free KHI molecules will be provided by the bulk phase. So and then eventually you will get the equilibrium for these two equilibrium constant. So when that happens, the more free KHI in the bulk phase will be proportional to the free KHI molecules on the surface, and because that is directly linked to the both the sites, so it will be also proportional to that nucleation rate. So if that framework stands, then we can base on that framework to work out the scaling between experiments and yeah. So here I'll like to define the nucleation rate NJ as always, and then define this scaling factor beta as the ratio between total moles of KHI in the liquid phase over the gas-water interface area. And then here I picked two experiment cases, A and B, which are both in 0.5% of KHI concentration, and they have different liquid loading, 100 ml and 300 ml, and the scaling factors of them are 1.3 and 6.4 respectively. So if we using this equation to scale them, which is saying the area nucleation rate times the scaling factor will be always the constant for every experiment happening here. So which is also saying when you have one nucleation rate from one experiment case, then you can use that scaling factor to predict another case. So if we apply that to our existing data with KHI, so that's what happened. So those, as you can see, those KHI with different concentration, with different loading, they actually reconcile well. And you note that all the experiment data from HPS alpha as well as the path data was scaled to the case of 0.5% of KHI in 300 ml liquid loading. So the nucleation rate can both reconcile with this technique. So I'd like to take one more step further. So can we predict the induction time with this framework? So if to do that, I may just do a little bit rearrangement of this equation. So that's the equation here. And then we move that area to the bottom of the scaling factor beta. And that's the form we have now. And then here, J apparently which is directly linked to the induction time. And then we got new scaling factor X, which is beta over the area and the differential scale. So if with this new scaling factors, if we plot induction time against that new scaling factors, and that is what happened. So as you can see, all the induction time, mean induction time points from different KHI concentration, different liquid loading, they're all aligned together, reconciled, and then they have a linear fit with some degree of uncertainty, where the gray area is showing uncertainty of this case. So if that is true, then whatever liquid loading or whatever concentration we have, we will able to use that linear fit and the uncertainty to predict the mean induction time. So here we pick 200 ml of liquid loading with 3 different concentrations of KHI. So 1.0, 0.1, 0.5, and 0.2. And we use that linear fit I showed previously to predict the mean induction time for these 3 cases with 200 ml liquid loading. The predicted mean induction time is showing in red font here. And then what we actually, the result of we measured induction time, boom, is showing here in green font. So the numbers for 3 different cases are actually within the uncertainty bar and then agree with the prediction very well. And if I show that result as a plot or graphically, then you can see that 3 points within the uncertainty bound and then align with that linear fit or the prediction line as well. So here, the induction time can be predicted with various KHI concentration and liquid loading in pipe alta. So it seems solve that KHI scaling problem here, but unfortunately there are some more challenges to be overcome. So in this part, I'm showing green one is the prediction line from pipe alta, and the HPS alta is showing in pink. So the induction time data in HPS alta sharing very same trend as pipe alta, and the slope of this linear fit is very close to each other, but the problem is they are not quite overlapping to each other. So probably there will be some missing information or something need to be updating with this framework. So as the way forward, more data equation will be required for both apparatus and then for different concentration and subcoolings as well. Okay, so wrap up to this talk here. So I've demonstrated how our pipe alta system experimentally investigate system size scaling and demonstrate the confirmation of gas water interface area is more appropriate system size scaling for KHI-free system, and also the new KHI scaling framework, as well as how you predict the induction time with those, and then demonstrate that the induction time is proportional to KHI density here, but not only just the system size itself. And as we go forward, more induction time data equation will be required for verifying and upgrading this scaling model further. Okay, thank you.